Yeah. So welcome everyone to the first Mathematics of Motion talk for this semester. Today we're happy to have Daniel Ingebretson, who will talk about the house of dimension for Kuperberg minimal sets. So Daniel.
Okay, thank you. So thanks for everybody coming and for inviting me to talk. So I'm planning to just give kind of a pretty broad sort of informal talk of some work that I did a few years ago. So please feel free to interrupt at any time. Hopefully I can just give you guys some pictures and show you guys some fun math, and that doesn't get too technical. So the story begins actually with the hop vibration. So you guys are probably familiar with this. So you can think of tracing a point along this two sphere, and then the fiber over the two sphere is going to be some circle. And this actually comes from, and so those circles are sort of beautifully intertwined in these sort of torus shapes, right? So these circles actually come from the orbits of a flow. So the hop flow, if you think of the three sphere as in complex two space, the orbits of this flow are the fibers of this vibration. So since the fibers are all circles, of course, so that means that every orbit is closed, right? So Seifert showed that if you bump this flow a bit, you change it a little bit, the periodicity doesn't get destroyed. And so he asked this rather innocuous question, whether this always happens on the three sphere. And this gave a lot of subsequent work, but there was the question is a little bit vague. So the subtext was that you could ask this question for various regularity, like smooth flows, C1, continuous even, right? So one reason why you might think that periodic orbits are sort of common are some sort of classical things from foliation theory and dynamics. So one thing might be in 3 dimensions, you don't have a lot of wiggle room. So if you have a codimension foliation on, say, S3, and you have a vector field that's transverse, you have to have a closed orbit. There isn't enough room to destroy a closed orbit. If you have any, let's say, C1 flow on a closed manifold, and you perturb it, you can perturb it arbitrarily small to obtain a flow that has either a singularity or a periodic orbit. So if you're looking at only non-singular vector fields, then this closing lemma will tell you that your generic vector field is going to have a periodic orbit. And then a little bit later, Katak sort of famously applied the ideas of Payson theory and Lyapunov exponents to study surface diffeomorphisms. So his theory, his theorem, if you look at his paper, doesn't really talk anything about flows on 3 manifolds, but if you take a section, if you take a local section to a flow, you get a diffeomorphism on a surface. And his theorem is that if you have positive topological entropy, then you not only have a periodic orbit, you have an entire hyperbolic set, which supports some measure with non-trivial Lyapunov exponents, and therefore you have infinitely many periodic orbits, and you have all the nice hyperbolic dynamics behavior. So it's kind of, you would expect these sorts of aperiodic flows to be pretty rare, given this sort of paradigm. So the way that people attacked the Seifert conjecture, if you're trying to disprove Seifert's conjecture, you're trying to come up with a flow that has no periodic orbits. You might try to do it in a local fashion. So first of all, you can take a vector field on S3 that has finitely many periodic orbits. And you can do this by looking at the, let's say, the gradient of a Morse function on S2, and then lifting it under the hot vibration to a vector field on S3. And you can do this. It's sort of a standard construction to get finitely many periodic orbits, and then you can try to break the periodic orbits. So to break an orbit, you need to glue in some sort of a local dynamical system, and you have to do this with some care. So gluing in this sort of, so first of all, you need to glue on the level of the manifold, right? And then you need to show that the flow can be made so that it agrees with the global flow on the boundary of the manifold and in a neighborhood of the boundary. And then inside the plug, you're going to have some kind of other behavior which you're going to try to specify. This is the general idea of trying to attack this conjecture. Okay, so there's a lot of different plugs. I guess the oldest one is due to Wilson. So the Wilson plug is very simple. It's just the product of an annulus with an interval. Or if you like, it's a rectangle times a circle. So for a plug, so again, it's a local dynamical system that we're going to glue into a global system, right? So I've told you what the manifold is. Now I need to tell you what the dynamics are. So the dynamics are, you should think of the lower annulus down here. Can you guys see my cursor down here? Okay, so you should think of the points entering in this lower annulus and then exiting in this upper annulus. So the flow is from bottom to top. And inside you have two periodic orbits. So these guys are just going around, and you need to specify the flow inside somehow that agrees with this. So I want somehow this is going to fit into a vertical flow on the outside, so vertical going from bottom to top, but then it needs to sort of interpolate to also account for these periodic orbits. So to do that, you're going to have a sort of a helical flow. It's going to spin around, and the rate of spinning is going to be relative to the proximity to these periodic orbits. So at this point, you should be a bit lost. So let me show you a picture of the orbits. Before I show you that, one important property of this plug is that it's called a mirror image plug. So this really helps you glue in this local system into the global one, because wherever a point enters in the bottom, it's going to go into the plug and it's going to do something, and then it's going to exit at exactly the same point at the top. And what's more, the flow lines are going to be symmetric over the central annulus. You can think of an annulus right in the middle of this plug, and there's going to be a symmetry there. So let me show you some pictures. If you enter pretty close to the outer boundary, then you're going to spin in this way until you get up to that center annulus, in which case you're going to exactly turn around and then retrace your steps so that you have some symmetry. And you can see that you're going to exit at exactly the same point as you entered. Now, if you're closer to those periodic orbits, like I said, your rate is now going to speed up. And if you're right on those periodic orbits, if you enter at a critical radius, value, then your orbit is trapped. You spin closer and closer to those periodic orbits and you never get past. So that's the idea of the Wilson plug. And if you start with a flow on S3 that has finitely many periodic orbits, you can kind of homotope those periodic orbits so that they enter the Wilson plug at the critical radius, and then they spin up to that trapped orbit, and in backwards time, they're going to spin down to this guy. So what you're going to get is a minimal set where, so again, in the global, we don't have a global picture yet, but in the local picture, inside this plug, we have all the orbits are collecting on these two periodic orbits. Everything else is escaping through the top of the plug. Okay. So let's go back to Seifert's conjecture. So Seifert asked about S3. So he was specifically asking about a 3-manifold. But you can ask the same question about a 4-man or a 5-manifold or anything like that. So Wilson's plug is actually what I wrote here, this plug, which is the product of an annulus, or if you like, a rectangle with a circle. You can generalize this to higher dimensions. So you can have a rectangle times a higher, like a torus. And if you do that, then you have more wiggle room to destroy periodic orbits. So using higher dimensions, plugs in of such shape in higher dimensions, Wilson was actually able to disprove the Seifert conjecture for dimension greater than 4. And greater than or equal to 4. And what he did is he funneled those orbits that are collecting. So you see in dimension 3, the orbits are collecting on these circles. Dimension 4, they're going to collect on tori, on 2 tori. And then you funnel those into irrational flow on the torus, which will never escape. So you have enough wiggle room that you can break periodic orbits. So Schweitzer basically made a huge landmark progress on this conjecture. He disproved it in the C1 case in 1974. And what he did, he also used a plug, but he used a pretty tricky construction with a. He did not use Wilson's plug. He used a more delicate construction. So he started with, he blew up, or he suspended a Dangerois diffeomorphism to get a Dangerois flow on a 2 torus. And then he glued in 2 copies of that. And then he had a flow that went from one minimal set to the next and then back. And using the Dangerois minimal set, he was able to break these periodic orbits. But the problem with that is that the Dangerois diffeo cannot be made C2. So this was purely a C1 construction. So basically there was no progress made for a long time on that because it didn't really seem like it would work. And then Jenny Harrison sort of shocked the whole scene when she actually improved Schweitzer's regularity with a crazy embedding of his plug. And it's a very, very complicated paper. I can't read it. I don't understand it. So really, this was kind of the end of the road for this approach. There was really no way to make this C3 or higher regularity. But it wasn't very much longer that Kuperberg solved this conjecture for C infinity. And the way that she did it was quite different. So Schweitzer's example, going back to Schweitzer here, was this tricky construction. Not as tricky as Harrison's, but still pretty tricky. But actually, Kuperberg went all the way back to Wilson. went back to the Wilson plug in the three-dimensional Wilson plug that I showed you. This guy. So this simple plug, which was not enough to break periodic orbits in dimension 3, it was only good enough to cut it down to 2 periodic orbits, right? So what she did is she just came up with an ingenious way to modify this Wilson construction. So in contrast to the Harrison and Schweitzer papers, Kuperberg's paper is very short. And it's deceptively simple, and it seems to have a lot of possibilities for modification. Not a lot of possibilities, but it's not quite as specific to the assumptions as Harrison's and Schweitzer's are. So it's like I said, it's deceptively simple. There's some complexity lurking underneath the surface, which we want to explore a little bit. Okay, so what's the general idea? So remember, the Wilson plug is a annulus cross a interval, right? So what you do is you twist that annulus into a figure 8, and then you pick 2 regions in the annulus, and you do a gluing procedure. So you glue them back into the plug itself. So you take a quotient under some identification map where you've deleted some neighborhood of the periodic orbits inside, and then you glue this in. And of course, when you do that, there's some care that you need to do. So just like, I'm not going to tell you the details, just like back at the beginning when I told you guys about the idea of just inserting a plug, right? There's some care that you need to take. To do that, you need to make sure that it's on the boundary. You need to put in a bump function that bumps you from one dynamics to the next. And so I'm not giving you all the details there. But it's a genius idea because, if the point of a plug is to break the periodic orbits, the Wilson plug fails to do that because the Wilson plug contains periodic orbits, right? So Kuperberg's genius idea was to actually destroy the periodic orbits inside the plug using the plug itself. It's a staggeringly creative idea, and it's even crazier that it works. So it's not trivial that it works. You need to prove it, and her proof is beautiful and very short. So that's the idea: is you twist. Remember the dynamics in the plug here. Before I embed this, the dynamics are going from the bottom to the top, right? So she puts in a half twist on each one so that the dynamics, when you insert it, will agree with the dynamics inside the plug. And so now this periodic orbit is going to go in the bottom of this surgered region, and that's going to again break the periodic orbit. It's now going to go into this quotient plug and wind around in there somewhere. And the proof shows that not only does this, number one, not only does this break those periodic orbits, but it does so in a way that doesn't create any new periodic orbits. So it's a beautiful construction. And like I said, there seem to be some choices that you can make, some modifications that you can make. And one of the key points is the germ of the insertion map near the critical orbit. So I'm going to talk a little bit more about what I mean by that. So what I mean, let me just show you on this picture, what's going on right here where you see my cursor is going to be crucial. Okay, what is the shape of the insertion of this part that I'm gluing in here? Okay. Okay, we'll get into that in a minute. Okay, so the plug itself is pretty complicated to look at. So what you can do is look at the inverse of this twisting map. So you can just view it as an annulus that doesn't have this double figure 8 twist into it, but still has those insertions. So it's very tricky to imagine the dynamics on this guy now, because you still have those spinning orbits that I showed you earlier, right? That are spinning, and the closer and closer you get to those periodic orbits, the faster and faster you spin. But now, when you get close to these insertion guys, if you hit one of these insertions, this region is now in the quotient identified with another region in the base over here. So when you hit this insertion region, you are now going to reappear in the quotient in the base and then keep spinning. So you can imagine the image of this red periodic orbit under the insertion map. The flow of that is now going to come out of this base and then go back and spin around, and then it's going to hit this, and then it's going to come back out. So it's going to start winding in a dense, crazy fashion. And it's really hard to keep track of what's going where in the quotient, the dynamics on the quotient. Okay, so I mentioned that there are some choices that you can make in the Kuperberg construction. So Herder and Reckman in 2016 really explored these choices. They said, what's kind of the least that we need to do, we need to assume so that we can get Kuperberg's construction to work? How rigid is this construction? And it turns out it's pretty flexible. And they called these assumptions generic. So their paper is about generic Kuperberg flows. And they had a lot of theorems. One of the theorems is that these sort of lie on a continuum of hyperbolic behavior. So there is a one parameter family of these plugs. So that right at dead center in the middle, you have the Kuperberg construction. If you bump it a little bit to the left, you have the simplest, so sort of Wilson construction, where you have two periodic orbits and everything else escapes. Entropy 0. Once you hit Kuperberg, all of a sudden those periodic orbits explode. They break, right? And then you have this Kuperberg construction. If you bump it any further than that along this one parameter family, all of a sudden you have horseshoes. You have hyperbolic sets, you have positive topological entropy, you have, positive Lyapunov exponents, you've got, hyperbolic measures, you got all the hyperbolic behavior. So this was one of the reasons why Herder and Reckman really sort of started this project to explore these sort of complicated flows, was because, in their words, these flows sort of lie on the boundary of hyperbolicity. You want to explore hyperbolic behavior in flows. The Kuperberg flows are sort of right on the boundary. They're complicated, but they're not complicated enough to get positive topological entropy. It's kind of a paradox. But the Kuperberg flow itself has 0 entropy. That is a consequence of that Katok theorem that I showed you earlier. Okay, one thing that they couldn't break, they couldn't make it too loose of an assumption about, is the insertion maps. So the insertion maps are the shape of the maps. Also, I'll show you a picture here. The shape of the maps that are being stuck into the plug to break those periodic orbits. And what they call the quadratic insertion assumption is that if you look at the inverse image of a vertical line under that insertion map, so here's a whole strip of vertical lines. If you look at the inverse image of that, you get a parabola in the base. And you need this sort of shape in order to get aperiodicity. So I don't really want to summarize Kuperberg's construction because that would be a separate talk, I think. So what's really going on under the hood is what really makes her proof tick is called the radius inequality. So remember, when points hit these insertion regions and then reappear in the quotient base of the plug, their radial coordinate is now bigger. And you need that. So that is implied by this quadratic insertion property. And you need that for aperiodicity for the proof. So that was one. And so I'm not going to summarize the other assumptions under what are called these generic Kuperberg flows. There are some assumptions you need to make on the speed of the Wilson flow and the actual vector field near the boundary. There are some assumptions that you need to make, but I just want to point out, sort of emphasize this quadratic insertion is kind of the most important. Okay, so if you look back at the flow, if you look back at the Kuperberg plug, this sort of surgered Wilson plug, here are your regions and their inverse images under these insertion maps. And remember, in the quotient, these two regions are now identified. So that's what I meant by every time that you hit one of these regions when your flow line is spinning up, you again reappear out here, and then you spin more. Okay. So here's an example. Imagine that you're starting in the base, then you're going to flow up, and then you're going to hit that region, and then you're going to come out again in another section of that region, and now your radius inequality is going to be a little bigger. So when you spin up, you're going to spin out and hit that region at a slightly larger point, or who knows, maybe you'll miss that region altogether and keep spinning up to the top and escape, right? So there's a lot of possibilities here. So at the risk of making you guys go to sleep, I'm going to show you some of the symbolic dynamics. So if you're going to try to make sense of this picture, one way to make sense of these sorts of flows or dynamics in general is to code your space, right? Code your orbits. So if you look back at, let's take this orange rectangle, this orange rectangular region, and look at it sort of inflated here. And so this red point here is the intersection with this critical orbit. Remember, points are slowing down really right next to that one, okay? So these black dots are intersections of flow lines. So you can see that the flow lines are slowing down as they get close to the periodic orbit, and then they speed back up, right? That's just the speed of the Wilson flow. So this is one, you can sort of code each intersection with this local section of the flow, right? And that would give you some points, right, that correspond to some sequences that are going from 1 to m. And m is going to be the escape time out of this local section, right? Now, in the quotient, when you pop out in the denominator at a larger radius, now you're coming out on this region, say. And now your radius is bigger, which means that you climb faster. So you can see that your escape time here is now going to be less. And it depends on on your radial coordinate in this direction. So then you get a set of sequences, and in this case, you get 3 sequences before your radial inequality will now get you out of this entire, this little strip that I chose. So this is sort of a common construction, right? You take a local flow, you look at the Poincaré first return map, and you code your intersections. So there's some way of separating points. In some sense, these points here are different than these points here, which is why I'm using different indices, right? And it's coming from different values of what I'm calling the Kuperberg and Wilson pseudogroup. So I'm not defining the elements there, but the pseudogroup is just coming from the holonomy pseudogroup of so hold on, I haven't defined the lamination, so I think I've made a mistake in my slides. I jumbled my slides around. Sorry about that. You don't see a lamination there yet. I'll get to the lamination in a minute. So the Kuperberg flow has a holonomy pseudogroup, which is just the holonomy of the foliation given by the flow lines, right? So again, this is just a Poincare first return map to this section, and it's local in nature, right? So what we can ask is, so this is kind of a picture of individual orbits, right? But if you try to follow individual orbits, you start to get a bit dizzy because there's a lot of possibilities for your orbits. So you might instead run your time to infinity and ask where your orbits are limiting onto. So does this have some sort of minimal set where orbits are collecting? And this actually turns out to be, going back to Kuperberg's construction. So in the same year that her paper came out, Gies wrote a Bourbaki seminar. So a lot of people were really stunned by her construction, and a lot of people started studying it. And one of those people was Gies. So he suggested that, and he purported to have a proof, even though the proof is more of a intuitive motivational idea instead of a proof, that there's a minimal set in this plug that is actually a surface, a topological surface. And he had kind of an enigmatic picture here, which was generated by some computer program by a guy named Bruno Sevenak. But he didn't really expound on where he got this picture or what relevance it really had. So it wasn't until 2016 that a full proof and rather technical proof was given. The technicality of the proof is really coming from the generic assumptions. So even in these loose assumptions, you still get a minimal set that is a topological surface. But it's embedded in a crazy way. So Herder and Reckman refer to it as a zippered lamination. And it really defies, it's very difficult to imagine this thing. But locally, it is a surface times a Cantor set. So it's some fractal, right? So if you have some fractal in here, you might ask what its dimension is. So this is our result, is that if you are under these generic assumptions, your Hausdorff dimension is strictly between 2 and 3. So what does this mean? This means, generally speaking, going back to this product structure, if you have a product structure like this, that just means that you have a honest to goodness fractal, and by the choice of some transversal to your lamination, your Cantor set is dimension strictly between 0 and 1, and then by your product structure, because your minimal set is locally the product of a surface, then you get your dimension between 2 and 3. So here is a picture of that minimal set, so you can compare it with the previous slide. So it looks pretty similar. So what sort of tools can you use to calculate Hausdorff dimension? Right. So I'm going to sort of go off on a tangent here and so forget everything about the Kuperberg plug and the Wilson plug and all of these laminations. Now let's just think about Hausdorff dimension of fractal sets. So this is sort of classical stuff. So maybe you guys have seen this before, but I'm just at the risk of, in case you haven't, I'm just going to show you. So sort of classical fractals are attractors of iterated function systems. So you can take a set of maps that are acting on some subset of Euclidean space, some nice subset, and you want them to contract. They're contracting, and they have some regularity. This is not a classical assumption, but we will assume it because we're going to need it in a minute. This is a classical assumption. You want some separation condition, okay? So you want their images to be disjoint or disjoint up to some open set inside. So they can overlap, but you need an open set whose image is disjoint. So they can't overlap too much. And this is an extraneous assumption. Probably most of the iterated function systems that you have seen are finite. So you have finite number of maps. But there's no reason to assume that. You can have an iterated function system with infinitely many maps. If you have finitely many maps, then this condition is implied by C1 plus alpha. But if you have infinitely many, you need an extra assumption. So I'm telling you infinitely because I'm going to need infinitely in a little bit. I'll show you. Okay, so every iterated function system has a unique attractor. So this is some sort of self-similarity condition here. And you can prove this just using some fixed point theorem. You can show that your maps, since they're all contracting maps, they're also going to contract the Hausdorff distance. And you can use that notion to set up a operator on the set of compact sets with the Hausdorff metric, and then the unique fixed point of that operator is going to be this so-called attractor. That's a little bit unsatisfying. You just have some existence of some fixed point. So instead, you can actually write it down, right? This is how most fractal sets are generated if you're trying to program it on a computer. You have these images of these sort of iterated, recursively constructed images of your space under your contracting maps, and then you take the intersection of those. And you can also use this construction to get a coding to your space. So your fractal is now coded by a sequence space. And this assignment is well defined using the Cantor intersection theorem, right? You have some nested sequence of closed sets. So this is a singleton. This is again using the contraction property. You couldn't define this if your maps were not uniform contractions. Okay, so a classical example, of course, is the Cantor middle third set. This doesn't really do it. I mean, most IFSs are a little more interesting than this, but I had to put this in there just so that we all know what we're talking about. So in this case, you have two maps, and you have the ternary Cantor set is now, you have a coding to the one-sided shift on two symbols, right? A little more exotic of an example is you actually have a countable. So I have a typo here. This should be I in the natural numbers. So this is a countable collection of maps generated by 1 over I plus x. And in this case, you get an infinite iterated function system, and its attractor is all the irrational numbers in the interval. So this isn't hard to believe if you just think about composing these maps. If you composed a bunch of these maps, you'd just be generating a continued fraction, right? And it's not hard to see that you get all continued fractions this way, and every, infinite continued fractions, and every irrational number has an infinite continued fraction, right? Okay, so now so far we haven't used regularity, right? We assumed C1 plus alpha regularity. If you assume this, then you actually get what's called bounded distortion. So this is sort of the starting point for what's called the thermodynamic formalism. So the thermodynamic formalism is sort of this injection of ideas from physics into fractal geometry that was started by Ruel and Sinai and Bowen in the 70s. So the idea is that classical thermodynamics is sort of the study of probability measures on your space. Instead of studying all points in your dynamics, you just study probability distributions of points. Well, it turns out that the probability distributions you get are very nice. And if you're going to try to estimate the Hausdorff dimension of something, so think about the Frostman lemma or the mass distribution principle, you need nice probability distributions on your space. So this was realized by these guys, Bowen and Ruel. And so a lot of the terminology coming from here is borrowed directly from physics. So for instance, the pressure function. Pressure means a lot of things in dynamics. So what I'm giving you is just the version of pressure. Pressure should depend on some potential. So I'm not telling you a potential. So this is just one version of a very flexible notion in thermodynamic formalism. For iterated function systems, this is what the pressure looks like. And it's a function of t. It's some real valued function of a real variable, and it's continuous, convex, and strictly decreasing, so it has a zero. And Bowen's theorem is that zero is exactly the Hausdorff dimension of the attractor of the iterated function system. And he originally discovered this when he was looking at limit sets of Fuchsian groups. So his paper, this was one of his many extremely influential papers. And this one was actually published posthumously. It was after his sudden death. So in retrospect, almost every known formula for Hausdorff dimension of fractal sets, there's usually some Bowen equation hiding behind the scene. So even in the case of just linear maps of the interval, say, like the middle thirds Cantor set, Bowen's equation reduces to an equation that goes back to the 1940s, which is due to Moran, and it's the sum of your contraction coefficients raised to the power of t is equal to 1, and the solution to that equation is the same as the solution to this equation. In this case, for the middle thirds Cantor set, it's log 2 over log 3. So it's some vast generalization of this sort of idea to nonlinear maps and more complicated situations. Okay, so iterated function systems have attractors that are some fractal set. But the coding of a fractal set, a coding of the fractal set of the attractor of the iterated function system is an alphabet of right infinite words that are all admissible. So basically, if you have sequences of maps here, you can compose these maps whenever you want. You can compose any two maps can be composed. For the purposes of dynamics, if you're trying to do symbolic dynamics and code some complicated fractal set, you may not always be able to compose these maps. So instead of composing maps that are defined on some of the same base space, you can instead do something called a graph-directed system, where now so think of a graph whose vertices are spaces and edges are maps. And so a composition of maps like we've been doing up to now, like over here. So here, a composition of these maps is now going to correspond to a walk through your graph. And you can only walk along admissible edges, so you need to be walking along some terminal and then a terminal to initial segment of your graph. So I'm not giving you all the details. I should, but I'm not. The details get a bit technical, so of these generalizations. But there are many papers about these sorts of things, and they're better for coding fractals that have more irregularities. So if you like, you can think of the middle thirds Cantor set. Go back here. And just imagine if over here we started dropping out terms, right? So let's say that when I get to here, when I get to the second generation, that I just throw this one away. Okay, that would correspond to, say, forbidding the word 0, 0. And then let's say in the construction of the Cantor set, now I forbid all words 0, 0. So what I'm going to get is some subshift of finite type, who is given by, again, some set of forbidden words. And the coding, the image of that coding, or the image of that space under the coding map, is going to be another fractal, but it's going to be sort of a leaky fractal, a fractal that is missing parts of it. And you're not going to see all these branching trees. You're going to see some of the trees, some of the branches on the tree have been pruned away. So this is more conducive to coding dynamics, where you don't, or your orbits aren't always recurring. Sometimes they disappear or they go somewhere else. Now, if you have some care, you write everything down, you still get an attractor of these sorts of systems. And so you can, and the attractor is still going to have some fractal structure, and you can try to find the dimension of it. And there's still a Bowen equation for these sorts of things. So for example, there are graph-directed systems. And so these are Markov systems. So their base coding space is some set of forbidden words. And graph-directed means they're a walk on a graph with finitely many vertices, but possibly countably many edges. Those are graph-directed systems. And they have applications in, let's say, expanding maps on manifolds or in complex dynamics. They also have applications for group actions. So limit sets of Fuchsian groups, Kleinian groups, these things can be coded using graph-directed Markov systems. If you have infinitely generated what are called Schottky groups, you can code those using pseudo-Markov systems. So pseudo-Markov systems now allow for the possibility that you have infinitely many vertices in your graph, in addition to infinitely many edges, and it's a bit more technical. So this is, this is relatively recent stuff, and people are still working on these sorts of generalizations of iterated function systems and their applications to fractal geometry of various types and dynamics and number theory. But a common denominator to all of these constructions is nesting. So you have a complicated sequence space that you need to find. If you have dynamics, you need to find it. If you're starting with an iterated function system or its generalization, you impose it. But you still have some nesting. So that comes from the contraction, and for the iterated function system, you have the same x here. But if you vary your x, you vary your base, you still have some nesting structure that nests down and approximates your fractal. So I'm harping on this theme of nesting and on symbolic coding, because those two ingredients are what I'm going to use to try to get back to this minimal set in the Kuperberg plug. So what does all of this blah, blah, blah of fractal geometry and iterated function systems and Markov systems have to do with the Kuperberg plug, right? Who cares about iterated function systems? So what you do is you use this theorem of Herder and Rechtman. So again, if you go, if I went back a few slides, you'd remember that they proved that there is a minimal set, a unique minimal set that is a topological surface. And so your minimal set has, and it has the structure of some lamination inside the plug, right? So orbits are jumping around and zigzagging and very complicated, but they're collecting on this crazy two-dimensional surface that is embedded in the plug in a wild way. So not only did they prove that, but they also gave a characterization of that minimal set. So there's actually a single curve in the plug. So I could show you the curve. It's coming from what's called the Rabe cylinder inside this plug. So that's the cylinder in between the two critical orbits in the inverse image of the insertion maps. So you can just imagine taking this curve and flowing it under this quotient, under the flow under this quotient, on this quotient plug, and you get some ribbon, right? You have a curve and you're flowing it, so you have a whole interval's worth of flow lines, which is tracing out some ribbon that's winding around in the plug. And as that goes around and goes through these insertion regions and reappears in the base of the plug and keeps winding, it starts to trace out the surface times a Cantor set sort of shape. So to try to understand this thing, you decompose it by a level of insertion. So by level of insertion, I mean how many times, if we start flowing, how many times has this reappeared in the base of the plug and started flowing again? Each time it does, I'm going to get some new generation of my Cantor, of my minimal set. So I'm going to stratify this minimal set by level of insertion, just to try to if I can understand each level, then maybe I can put them together. So Herder and Rechtman termed each level a propeller. So it's a little hard to imagine these things, but again, you can think of it as sort of a surface that's winding around the plug. And as it enters these insertion regions, it starts to branch out. So you have sort of a tree of surfaces that are branching out. There's all this very colorful terminology for these things. So Herder and Rechtman called them propellers. Gies actually called them cauliflowers because like a cauliflower like has all these branching regions that get crazier and branch out. So I can't really top all this sort of great colorful language. So let's look at the first generation. Before we go through an insertion, let's just take this curve and let's flow it using the Wilson flow, which again just goes up and slows down if I'm close to the periodic orbits. So if I'm looking in just a local section, then I get some picture like this. And those curves are actually, you can actually write them down. You can generate them using, you can integrate the Wilson flow. So it's not difficult to do. And so you can actually calculate these things. So this is your M1 propeller. So this is level 1, let's call it. And they bound some regions, right? And the pseudogroup is contracting. So if you look at this propeller as opposed to this propeller, which is the image of the pseudogroup, one iteration, then 2 iterations, then 3, you can see that you can see that these regions are getting smaller and smaller. So that has some contraction property, which we saw earlier in the iterated function systems, right? We had some contraction there. And I've stopped this because my computer is bad, but this keeps going forever, right? So the point over here is getting really close to this periodic orbit. And so that means that my symbolic space that's coding these is infinite. It's the natural numbers. Now, if you follow each one through the insertion and then you flow that, so again, it's coming out the base of the plug in the quotient, which is identified to this region. Now you get some nesting. So each of the images is now nested inside the next. And I'm only showing one of these. So what you should imagine is infinitely many, inside each one of these, there are infinitely many red curves that are now collecting on. So these blue curves are collecting on the periodic orbit. In each one of these blue curves, there's infinitely many red curves that are collecting on this orbit, or on this point, and collecting on this point, and collecting on this point, et cetera, et cetera. And as they get closer and closer over here, they take longer and longer to escape. So you have contraction and you have nesting, which is kind of telling you there may be an iterated function system or one of its generalities hiding underneath the surface here. So what we want to do to figure out this Hausdorff dimension is to come up with some Bowen equation for the dimension. So the pressure is now going to be defined in terms of the derivatives of these holonomy maps. So these holonomy maps are coming from, again, successive iterations of the Wilson pseudogroup and the insertion pseudogroup, which is coming from that slide that I showed you about the symbolic dynamics of the Kuperberg flow. So you can look at the derivative of these maps, and then you can compose them. And when can you compose maps? Well, you would need to know some admissible words, right? So that's a coding problem that you need to solve. If you understand the pseudogroup well enough, then you can write down a subset of those admissible words that so a subset, you can contain your set of admissible words. You have some subset that you can quantify, and it is contained in another subset that you can quantify. So you can't catch it on the nose if you're talking about quadratic. You can linearize it and then you can actually calculate it. But if you're talking about quadratic, you can only approximate it. Same thing with the derivatives. You need to approximate these things. So what you get is error. So error gives you what I'm calling a generalized pressure function. But remember, we're trying to calculate these things. So if we can minimize the error, then we can actually calculate the value of this dimension. And of course, the error is going to depend on your parameters. So remember, we're talking about generic Kuperberg plugs here. It means that we have some parameters that we haven't fixed yet. If you vary those parameters, that's going to affect the speed of the flow, which is going to affect not only the admissible words, but also those derivatives. So your dimension is going to change. So if you fix a model, you can calculate the actual dimension. But if you are just looking up to genericity, you can show that that dimension is bounded away from 3 and 2. So you get in between 2 and 3. yeah, like I said, there are parameters you need to fix in order to calculate that. And then you look for zeros of those generalized pressure functions. So that's a little bit about the strategy of the proof, and I will stop there.
Okay, so first of all, let's everyone thank Danielle. It was a very interesting talk. So, are there any questions? Okay, so I have one question.
Yeah.
You spoke earlier about the Kuperberg flow being on the boundary of complex dynamics.
Yeah.
I mean, I know there. I mean, does it, in some way mirrors, the theory of sorry, let me say it otherwise. Does it in a way mirror, known bifurcation theorems from, say, flows or diffeomorphisms, or?
That's a good question. I don't know. So let me go back to this slide. So I don't actually know this construction too well. I worked mostly on the generic Kuperberg stuff. If you bump it, yeah, here it is. Yeah, if you bump it, then you get horseshoes and hyperbolic sets. I'm not sure if you can recover. So you're asking about like the actual bifurcation scheme of this thing, like
Yeah.
different, swallowtails and dovetails and this sort of thing like that.
Yes.
I would think that. So I really don't know. That would be interesting to ask. So the paper, I may have miscited this result. So Herder and Reckman's original paper in 2016 came out. It's kind of a massive, it's like 170 pages or something like that. But they had a second paper that they called I think it was something like at the boundary of hyperbolicity, at the boundary of chaos or something like that. And it was sort of a provocative title. So it could be that they elaborate on it in there, but I don't think so. That the actual like topological aspects of the bifurcation, I don't know if they are known. I'm guessing not, just because the Kuperberg plug itself is so complicated that just showing that you get topological entropy here, 0, or get positive topological entropy in periodic orbits is already kind of tricky to prove. So showing how you get them, or in what sense you get them, I would guess they didn't do. That's just my guess.
Thanks. Are there any more questions? Okay, so if not, let's all thank Danielle again.
Thank you guys for having me. This was fun.
Thank you for the excellent talk.
Yeah.
Was very interesting.
I'll enjoy attending the next talks. You guys have one coming up in a few weeks, or?
Yeah, we have Passover break, so I think the next one will be in 2 weeks.
You said a couple of weeks or 3 weeks?
Yeah, 2 weeks, I think on the 18th.
Okay, sounds good. I'll be there.
Great.
Great. We'll see you then.
Okay. Thanks again, guys.
You're welcome. Bye-bye.
Bye.
Okay, bye.